Hello?
Hello.
I don't know. Can you hear? So
Yes.
okay. So now works. Okay.
Thank you.
Okay. So Feynman, beginning of a scientific journey that accelerated over the last few years tremendously, mostly during lockdown. And I think this is part of the reason that the dissemination of these this revolution in research results, of this revolution in realization of actual computational machinery hasn't disseminated the same way it had without a pandemic, essentially. So I think there's something to catch up. So, but still, quantum is omnipresent, right? Quantum is there in books, quantum for babies, then it's in the media outlet, news, and so on. It's like it's kind of present in various ways. And I mean, don't make any mistake. Even the Deutsche Bahn is looking now for quantum experts here, right? And if such a conservative company like the Deutsche Bahn is actually looking for quantum experts, this is a field that is here to stay. So if you have a look where a quantum or some sort of quantum advantage, or at least a beneficial contribution of quantum computing is anticipated, Gartner has made so a consultancy company has made a study, and you can see different science areas where quantum computing could be beneficial. Quantum chemistry, for example, calculating bound states, performing optimization tasks on molecules and so on, drug design, all these kind of things. Then also logistic problems falls also in an optimization category, traveling salesman problems, and so on. Another area is physics, and this is what we want to talk about today mostly. So condensed matter physics, which anyway has discretized systems, and quantum dynamics, then particle physics, quantum optics. Areas where directly also quantum advantage is foreseen is Hamiltonian simulation. I will talk about this a little bit more in a second. We would like to be able to calculate also non-perturbative physics rather than just focusing on algorithms for perturbative physics. And entanglement, we have heard a lot about entanglement over the last 1.5 days. The thing that drives a lot internationally is quantum information technology, teleportation, secure transmission of information, the quantum internet, as they say, how to break or encrypt information, store information, and so on. This is all part of a highly active research environment. And last but not least, machine learning. Machine learning has also been rapidly popularized over the last few years. And the question would then be, of course, how can you actually contribute within the quantum computing paradigm to improving machine learning and to improving on the tasks for machine learning. This comes, of course, with a rapid and significant investment. An exponential growth of investment is anticipated in all of these areas: energy, transportation, healthcare, and so on. And in the public sector, we have seen also the foundation of a lot of labs across the US, also Singapore and Abu Dhabi, as I heard yesterday, has rapidly expanded. So CERN and so on, a lot of places that are now focusing on how to utilize the quantum computing paradigm for physics and for the development or for the improvement of our understanding of nature. Okay, before looking into the actual applications, if you actually want to run this, if you want to design your own codes and submit it somewhere, there are essentially 3 quantum computing paradigms that allow cloud access these days already. So discrete quantum gate computing, it's a digital approach to quantum computing. Digital means you actually encode it in numbers, like you would do classically. This is considered to be a universal quantum computing approach. Of course, depending on which gates you are allowed to use on your quantum computer, but this can be a universal approach to quantum computing. And the advantage of this discrete gate quantum computing, if you intend to work in this direction, is that there's a plethora of algorithms and technical support already online. IBM has its own front end and allows you to access a fairly large number of qubits, up to 100 for free these days. So this is quite impressive. Then there's continuous variable quantum computing, essentially based on photonic quantum devices. It's not universal if it's based on Gaussian boson sampling, but if you get access to the Q modes that they have and you can implement the gate operations that you need, it can be universal. Interestingly, it has an overcountable Hilbert space and could therefore be more expressive than other approaches, more efficient potentially. And then last on this slide, at least, it's quantum annealing. I'm going to talk about this as well. In the end, it's considered to be an analog quantum computing paradigm. Essentially, what you do is you encode your problem into a quantum environment. And then this quantum environment has some quantum dynamics that then processes your Hamiltonian with which you communicate with this environment using its intrinsic quantum dynamics. If it's quantum annealing and it's based on a Ising model, then it's not universal. So the trick here, the problem is, on the one hand, you get 7,000 qubits for D-Wave, from D-Wave by cloud accessible. This sounds really a lot. It's a very expressive system that you could potentially encode. But the issue is all your problems have to be encoded in terms of an Ising model to be able to run on the D-Wave devices. And this costs you to encode your problem in a very restricted form. It costs you a lot of qubits essentially to do that, and therefore effectively you will have not the, you will still have only a limited system to work with and to encode your problem with. A generic form for any quantum algorithm that we have is the following. So we have essentially some form of data encoded on a system, classical data X, for example, encoded as a state vector onto your system. And then the question is what we actually want to learn is the expectation value of a specific operator. This operator has to be unitary. And then you sample over the configuration space to get the expectation value for your operator. And this is, of course, a statistical statement, right? So to get the expectation value, you have to perform the algorithm multiple times, maybe 5,000 shots or something like that, to get a reliable distribution from which you can extract your expectation value of your unitary operator. And this needs to, of course, be taken into account when you consider efficiency of your algorithm, runtime of your algorithm, and whether it can compete with classical approaches. What you need to do then is encode this in terms of gate operations, as you see here. So your unitary operator, this would be a quantum gate operation. You have different registers. They could correspond to different qubits. Then you act, what you do is you always read from left to right. So essentially you have your state, you act with your operators, and the information flows from left to right. And then in the end you measure and you get some numbers out. Okay, and you can visualize this in the most simple way in terms of one qubit, which can be represented by a block sphere. So you initialize your state at 0, then you perform some unitary rotation into your state psi, and then you can perform a measurement, and this measurement projects onto 0 or 1 with a given probability. So everything here can be calculated. Obviously, it's just a rotation about a sphere, and then you calculate the scalar product, the projection onto 0 or 1, and the overlap is given by the probability of measuring this state either in 0 or 1. Now, for one object, for one qubit, this is of course kind of trivial, but the advantage is that you can build a tensor product of different qubits, so you quickly grow in the dimensionality of your Hilbert space. In terms of n qubits, gives you a 2 to the power of n dimensional Hilbert space. And because those are two spheres, it's quite expressive already at this point. So, yeah. High energy physics, I think, at least from what I would like to discuss today, has three major application areas with respect to quantum computing. One could be, for example, we are interested in particle collisions. So we want to smash protons together. We want to simulate what comes out of it eventually. Then the other thing is we have measured them, we have smashed them together. They are recorded in our detectors. So we want to analyze data. This goes then into the direction of quantum machine learning or machine learning. And on the other hand, what we would like to do is essentially not only follow a specific physical picture like a parton shower that has then been implemented on a quantum device, but on a more fundamental level, non-perturbative interactions and simulate field theories in a more fundamental way. So this would of course be interesting as well to do that on a quantum device. So we have now a three-pronged approach to look into whether we can actually use quantum computing beneficially for a better understanding of nature. Okay, let's start with why we actually probably have to do it and where we can actually expect the most likely quantum advantage. And this is interestingly very much following what Feynman outlined in 1982. Well, we are actually simulating quantum field theories. We are simulating quantum mechanical systems. So maybe we want to do this on a quantum device. Because what we find these days, doing it on a lattice, on a classical computer, in terms of lattice language, we encounter the sign problem, this infamous sign problem. So this is what you can see here for the QCD Lagrangian. If you, for example, have a chemical potential, and the same problems appear if you have a topological term, if you have a high density environment, multi-fermion interactions, and so on. What you get is essentially an imaginary phase that contributes to your action. So what you get is, to calculate your partition function, you will eventually have a complex phase if these things are present. And this will render your solution very, very difficult to calculate on a classical device, because what you get is you get these kind of oscillatory solutions. And to sample from these oscillatory solutions, when you integrate here over this relative complex contribution that you have in the action, is classically extremely difficult to calculate. So going into a Lagrangian, then expressing it in terms of the action, then putting it on a lattice, and what you want to do on a lattice, you want to sample from an exponentially falling function, e to the minus s, by going from Minkowski space into Euclidean space, doing a Wick rotation. So you actually calculate something that exponentially falls off if you don't have a relative imaginary phase in the action. However, if you have a relative imaginary phase in the action, then your Wick rotation doesn't help you, and you will be left with oscillatory solutions even after going into Euclidean space. And this is actually a very common problem for high baryon density, high temperatures, and so on. This is what you see here in this two-dimensional phase diagram. So it's something that people working on lattice gauge theories encounter these days all the time. And the solution was already written down in the 90s in some sense, namely by Hamiltonian simulation. So Kogut and Susskind formulated their way of performing lattice calculations in terms of expression of a Hamiltonian in the 90s. But back then, nobody, so it was essentially, it's a way to solve this problem, real-time evolution, as you see here on the upper right part. You start with psi 0, you act with your time evolution operator in terms of your Hamiltonian, you get a new state. This is real-time evolution. You don't perform a transformation from Minkowski space in Euclidean space, and therefore so you stay in real time. Now the thing is, this doesn't work well on a classical device as well, because if you do these time steps, your Hilbert space explodes. It grows exponentially. And so what you actually need is a quantum device. So this is an algorithm that is designed to be run on a quantum computer on the one hand, and on the other hand, it solves the problem that we now encounter on a classical device in terms of the sign problem, because it doesn't introduce the sign problem. So here is a clear pathway to a beneficial algorithm for quantum computing. And these days, of course, I mean, with these relatively small systems that we have on a quantum device, we are making horrendous approximations, obviously, to get anything on a quantum device in some sense, right? So all these gauge theories that are being simulated are usually approximated. Continuous symmetries on a discretized system are just very difficult to implement. And these systems are very, very small. So you have to make very crude approximations. But people are thinking now how to do this more efficiently, because there is a clear path. There's a clear path to a quantum advantage. Okay, so then there's the other part that I initially introduced, namely the calculation of particle collisions that we are really interested in. And we have a long history in developing full event generators, Monte Carlo event generators. with here a few names that you see here at the bottom. And all of these event generators, they consist of a couple of steps, essentially. So initially you have the proton. You start essentially with the hard process that sets your hard interaction scale. And then you do forward evolution, if you like. You do some backward evolution to get the PDFs right, but forward evolution in terms of a parton shower, going to a lower energy scale. And then at the hydronization scale, you form mesons, hadrons, which are then, of course, also short-lived, decay into long-lived particles, and so on. Now, in terms of quantum algorithms, the part that has been mostly developed was the parton shower part. There are a couple of papers here and there for hydronization and for the hard cross-section as well, but most papers and most publications have been made with the parton shower in mind. So let me just briefly outline what has been done in this respect. So if you look into the parton shower, which is this piece here in the middle, a parton shower is enhanced in two kinematic regions when the emissions are collinear or when the emissions are soft. So in these regions, you want to get it right because this is where the most emissions happen. So the cross-section is fairly large in these enhanced regions. And further, it factorizes. So the entire process, you could imagine that if this was a quantum mechanical process from 1 going to 50 or something like that, or 15, if you had to keep the full interference into consideration, this would be an impossible task. But fortunately, in these kinematically enhanced regions, also the amplitude factorizes into individual splittings. So suddenly you can describe this as a semi-classical approximation to a quantum mechanical process, and you can evolve the entire thing knowing the splitting functions and pseudocov factors. So all of the currently used parton showers essentially calculate the non-emission probability here using the pseudocov factors. Then they evolve in their respective shower time from one scale to the next, calculate whether an emission should occur. This probability is given by the pseudocov factor, and if an emission should occur, then they would make the emission, or so it's essentially a random walk process that is being done based on the probability of a pseudocov factor. So then, however, what this, as we said, doesn't do, because what these kind of classical parton showers don't do, because they factorize and don't take interference effects properly into account, then the Berkeley group here, Bauer, Nachman, and so on, they looked into interference effects and showed that if you had, for example, different flavor states internally, these interference effects, classical parton showers, current classical parton showers would not take into account. And they gave a toy model based on the parton shower pictures, a Yukawa model, where they showed that it can be efficiently simulated on a quantum device. So here, a quantum device has also an advantage over a classical algorithm. Of course, in a simplified form, but of course, this can be expanded. So what we looked into was then to expand it to an actual gauge theory while maintaining the benefit of this parton shower picture approach within the Yukawa model. And you can do this as well with specific gates that are designed for the parton shower to evolve in time. So you have a counting gate, emission gate, historic gate, history gate, and then you compare this with a classical example and you find very good agreement, essentially. So you can do this classically, you can do this quantum mechanically, because it's reasonably simple, very few steps. And then you set this up and you find this. It's very unimpressive, right, overall, because here at this point, it's only a couple of steps, 3 or 4 step parton showers without kinematics, just counting the number of flavors and gluons, very unimpressive. So the next step would then be, okay, maybe you can make this more efficient. One idea was then to look into quantum walks. So to contrast a quantum walk with a random walk, this is a distribution. The variance of a random walk is given by, so the variance is, scales with n, where n is the number of steps that you are using. You see, of course, if you have a classical object kind of goes one step right, then it thinks about whether it should go left back again or right, so kind of back and forth and so on. So very, very slowly, only it samples from very large position space, right? It's a very slow way of walking from one side to the other if you're relying on a random walk process. Now, for a quantum walk, it's different because you have a Hilbert space, you have a coin that flips and puts this entire thing into superposition. And then you have the position Hilbert space with a tensor product within. So you have interference taken into account and superposition simultaneously. And this then allows a completely different probability distribution for the quantum walker, which actually scales like n squared. So this means if you have something where you want to sample at large position space, the quantum walker does, of course, a much better job. So it's much faster, essentially, in exploring the entire phase space of your system. And for specific quantum walkers, it has been proven to get at least to get a quadratic speedup. It's very closely related actually to the Grover algorithm, and therefore this quadratic speedup is kind of what you would expect. So what we then did is we expressed the Parton shower in terms of this quantum walk picture. You have this coin operation, shift operation, memory, and so on. You repeat this over and over again, and suddenly now at least you can go to a realistic number of gluons, right? Previously we had like 3 or 4 objects overall, but now with a quantum walker that is much more efficient than the usual approach of implementing these operators and splitting operators and so on hard-coded. We can go and simulate easily on a fairly small device up to 10 gluons. Yeah, depending on the splitting quarks and so on as well. It's just a distribution that you would get. Okay, but still not good enough and still quite unimpressive because you can't use it. What's the point? So the next thing would be to actually include kinematics, because before we didn't have any kinematics. So it was still without kinematics. And what do, I mean, we want to study exclusive distributions for final state objects that have arisen from a proton-proton collision. Okay, so the next step is then you notice that the usual veto showers that are used classically cannot easily be implemented quantum mechanically. That's an issue. So just like before, just in the example I showed before with the Lagrangian going to the Hamiltonian description, here we thought about, okay, we have to change the algorithm that we are using. And actually, just like in the other case, there was a paper even earlier in the 80s where they promote discretized QCD. So in the veto shower, you have continuous variable over which you have to integrate and so on. But Gösta essentially wrote already a paper about discretized QCD in the 80s. And it turns out that this is actually something that is very well suited to be implemented for a quantum walk process. So what you do is, and there's a lot of equations going on, what you do is essentially you discretize it in the Lund plane. So you have kappa is the transverse momentum of your gluon. And in this case of your QQ bar system, so you look into the process at lab, A plus A minus, photon, Z or Z boson, Z decays to QQ bar. This is essentially this object here in the Lund plane. And then you ask yourself, this QQ bar dipole system can emit gluons and can radiate gluons. And it turns out that if they are collinear to each other, they act coherently. And this this can be proven showing or using the randomization group equations. So you can consider them to be one object, and then you can discretize your phase space according to these kind of discretized columns essentially. And discretized systems can be very nicely walked along using a quantum walk approach. And this is what you see here. So this corresponds to one one event where you have a QQ bar pair, it radiates off a gluon, the gluon splits again, you radiate another gluon and so on, and the quantum walker walks along these groves into the entire system and samples from it. And then you can calculate this, and you can actually first look into a simulator and see what you get out. And you see here a very good agreement between a classical simulation and a quantum simulation. For such a process, you will get very good agreements for your final state objects. And now you have kinematics. That's the advantage, right? So the kinematics are completely encoded in these growth structures. And then you can plot it, and after interfacing it to, say, Pythia for hydronization and so on, because this was only the Parton shower process, you can then get distributions out in kinematic distributions. And okay, you can then also submit it to an IBM device, and there it doesn't look as pretty anymore, right? So in a simulator, you have perfect agreement. on an IBM device without error correction or anything like that, you see it kind of follows the same shape and so on. But of course, there's big errors, let's say. And I mean, there are a few reasons for it, swap operations and so on. You lose coherence reasonably quickly. And this causes these errors. Interestingly, because you have a reasonable resemblance of the actual shape that you would like to see, if you look into the distribution and you now compare to actual Aleph data. So this is a comparison where you have run an algorithm on a quantum device and then compared to actual high energy physics data, namely the ILC data gathered, the lab data. I wrote ILC, lab obviously, ILC we don't have yet. So, so lab data obviously, and you compare with a classical implementation, which is this DQ-CD shower, and then the quantum shower run on the IBM Algiers machine. And so the agreement is reasonable. It's not perfect or anything, but we didn't expect a perfect agreement given these errors. It's still quite impressive to be able to run on a fairly small quantum device something that you can nowadays compare with data that has been gathered at actual high energy physics colliders. So the next step is now, we talked a little bit about simulating field theories, or at least yeah, the motivation for how to do that and why. But data analysis is, of course, one of the big points for high energy physics to resort to things like machine learning or quantum machine learning. On the one hand, we have a plethora of data at the LHC, and this puts us in a very, very different and a very privileged position compared to other science areas, right? We have plenty of data. We can generate pseudo data for free, essentially, on the one hand, and further, this data that we gather and that we generate is extremely well understood. I mean, there's no other science area that has such a level of complex data while having at the same time a theoretical prediction and understanding of this data to such a high degree as in particle physics. And this helps you on the one hand, of course, because now this is actually a hotbed and a very interesting playground to actually improve our understanding of these machine learning techniques on the one hand, but on the other hand, it also goes from right to left here on this plot. We actually need automated tools to actually analyze this plethora of data. So it's a symbiotic, relation between high energy physics and machine learning, mutually beneficial for both sides. What we often do is, just to connect with what I want to talk about now, what we often do is we do signal from background separation, and so supervised learning and anomaly detection are prime playgrounds for the application of machine learning techniques in high energy physics. So but before going there, I want to go back and resort back essentially to why I also started with protein folding. Every algorithm that we are looking into that is based on a variational principle consists of three pieces, right? You have an adaptable complex system. So if you look here into does this work? Probably. So if you look here into this neural network pictures that we have here, this is a fully connected neural network. The input layer would read in your data, your features of your events or whatever you feed in, and then it's connected to each of these following nodes in the next layer. So it's fully connected. What happens here is you wrap around an activation function. Each of these lines comes with a weight. Then you wrap around an activation function, and then you pass this on to the next one. So what you get out in your output layer is nothing but a function of functions. Right? It's a linear combination of functions with a lot of trainable parameters that make your system highly adaptable, highly expressive, and put you as in the first go into a position to modify this function at will. Okay, then what you need as a second step is essentially a loss function or some target function, something that tells your network what it actually is supposed to do. Like for the protein, essentially, you need to know what the energy minimum of your system is. So you construct with your loss function some way potential landscape and you want to minimize, or you want to find the minimum of your loss function. And in this minimum of your loss function, your algorithm performs what it's supposed to do, right? It has the smallest error and it knows what it needs to do best, essentially in the minimum of your loss function. And the question is now, just like for these proteins, how do you get there? There are different ways of getting there. Neural networks usually use some gradient-based optimization tasks to go into the ground state of the system. This requires you to have some form of smoothness and so on in your system. And this is what's mostly used. But these three pieces, they are there in tensor networks, and they are there in quantum computing as well. It's essentially the same thing, because it's the same thing for all variational approaches that you work with. And the interesting part is that this kind of optimization, you can do data analysis using this, but you can also simulate field theories. It's exactly the same thing. VQEs, for example, calculating ground state of bound systems and so on. Variation in quantum eigensolvers is VQE. But also things like solving differential equations, because in the end, all you have is a variational ansatz that is highly complex, that is tunable by you. And then you have a definite way of how to go into the ground state of your system and how to train your network. And this is, I think, important because this will link to what's going to come next. Let's have a look in comparison how the quantum machine learning framework works, say for a variational quantum circuit. So the first thing is we have classical data. In this example, this classical data is X. So now the classical data you have to put into a wave function in some form, right? You have essentially a tensor product of qubits and so on, which is your wave function, and you have to initialize it. And this is usually done by some form of encoding. One could, for example, look into angle encoding. So then you perform some rotations about one of these axes, for example, and your wave function then looks like this, where each of your features of your classical data corresponds to one qubit, or is encoded in one of these qubits. So this is what you see here. The next step would then be your unitary operator. This is actually your model with which you manipulate your quantum wave function that you have initially, and could look like this, for example. You have rotations on each of these registers, which correspond to a qubit. So you have trainable parameters here, alpha, beta, gamma, that can rotate your vector here about these qubits. And then you have a C0 operation. A rotation and a C0 operation entangles. It's like one puts in superposition and the other one does a C0, a conditional probability, boom, you have an entanglement. So this means since you entangle it between the different registers, you share information between the different registers. You can entangle many of these, but you initially only one qubit knew about the classical data that the one feature it was encoded in. But now you entangle the entire system, so now you share this information across the different registers and across the different qubits. And then in your last step, okay, so now you need an observable, right? The loss function that you actually have has to be defined in some way. And because you shared the information across different qubits, you could, for example, just measure one of them up here and calculate here the projection using this sigma z operator that projects out your eigenvalue plus or 1 or 0 essentially for your system. Because you share the information, there's also information of all the other features stored in the upper register, in the upper qubit, and therefore the projection on this can allow you to get some statement, whether it's signal or background. Then, as we said before, the third part is now something where you need to go into the loss function's ground state, right? You have to define your loss function. You have your network output, which is measured here and then put into your network output. And it's either you label it, say 1 or 0 for signal and background, and either f should be 1 or 0, depending on the features that you feed in. And you want to minimize the entire thing, the sum over all of your events, your batches, or your full epoch, is then this entire loss function. And in the next step, you have to update these rotation angles such that in the next go, so it's backpropagation essentially, and you do this classically. So you update your rotation angles in such a way that you reduce the loss function step by step, and you go into the ground state of this entire system. There are tricks now that you can play using Fubini study matrix and quantum gradient descent and so on. which make it faster because these networks are reasonably small and you know the geometry because you work with angle rotations and so on. You can exploit this, and this can help you to actually find the ground state faster of your loss function. And this is what you see, right? So if you compare now a neural network with gradient descent, a classical one, then a variational quantum circuit with gradient descent, and a variational quantum circuit with quantum gradient descent, then you see that the one with quantum gradient descent it trains extremely fast. So it trains out very, very quickly after only a few epochs, after having seen very little data as well. So this is what for 1,500 training events, which is already a small number, right? And for 500, it's even a smaller number, and it also works well and trains reasonably well here. So this is quite impressive. Then the ROC curves, they are very similar. And you can also put this on a quantum device. And because it's such a shallow circuit, actually performs quite well. The deterioration of accuracy is not too large. It's 1.2% between the simulator and the actual quantum device. So you can already now run this on a small scale device and essentially get a reasonably good result. So the other point was anomaly detection. Okay. And anomaly detection with machine learning frameworks, the most popular way of doing this is actually using an autoencoder. So what is an autoencoder? Because what we said is usually you define your loss function in such a way that you have to actually label your data, right? You say signal is 1, background is 0, and then you try with your neural network output to match either 1 or 0, depending on the input object was a signal or a background event. And so in a case where we do anomaly detection, where we only see background, only see QCD events, we don't have this feature of being able to label our signal. So what we actually want to see is we want to, based on the kinematics that we feed in and the features that we feed in, we say this thing here looks like signal. Or essentially this thing here does not look like background on which we trained, but something else. So it flags up as an anomaly. This is the idea. And to do that in terms of a neural network structure, you have to have something like, the idea is to have something like a latent space that has information bottleneck. So you start with your input features here. You do an encoder, which has a smaller dimension as on the output as on the input. So this puts, and then you ask the decoder to only look at the latent space, at the information bottleneck, and reconstruct the same features that you fed into the encoder. This means this part here and this part here, this is the goal of your algorithm, should be the same. But this information bottleneck here puts pressure onto the decoder, right? It shows it less information, it shows less dimensionality of information, and it can only perfectly reconstruct the input if the information bottleneck is the same size as the actual information bottleneck, meaning the independent dimensionality of information that you need to fully describe the signal events, or to fully describe not the signal events, but the background events that you fed in here on which you trained the autoencoder. So if the information space of your sample from which you train your autoencoder is the same as your latent space, you can get a full reconstruction, and then the loss function will be minimized because the loss is the difference between input and output. Okay, and then you freeze your training. You stop training. You found a reasonable setup for your background events. And because your signal events, they look different. They have different internal correlations between its features. It will not work and go through the, or it's less likely to go through the information bottleneck without a loss with the same decoder that has been trained on background to actually reconstruct the output exactly the same way as the input. This is the idea. So long story short, this is essentially the idea of an autoencoder. And well, there's a trick. I mean, the issue is we are now, if you want to put this onto a quantum device, we are actually supposed to work with unitaries, right? And this is not a unitary operation to start with a larger dimensionality and to have an information bottleneck on the other side. So it's not a unitary operation. The inverse, having an encoder and then a decoder, the inverse of a unitary operation is very easily calculated, obviously, right? Unitary is just the adjoint. Is the inverse. And however, then we cannot put any pressure into the entire thing, and this would amount to a 1, and nothing would happen, obviously, and we would not learn anything. So what needs to happen is you need to put pressure again into the system, and so you have these trash states, and you couple out information from this unitary. And then you have trainable parameters, and you hope if by training only on background that the fidelity here between input and output is large. So this is the idea of a quantum autoencoder. And you might say, okay, this can't work, but it does. And it does work actually quite well, surprisingly. So if you look and compare a classical autoencoder, this is your loss root mean square error of your loss function, essentially, or of distribution. And if you look here at your fidelity, you can again look into the training size that you have, and you are very insensitive with respect to the size of your training sample on how many background events you actually trained for your quantum autoencoder, whereas you have a very quick deterioration here for the classical case. So it much more depends on the amount of data that is being shown to the classical algorithm than to the quantum algorithm, which can live with much less data. And on the other hand, you actually, again, have this feature that you train super quickly and you train out super quickly. There's no overtraining, right? Here, you actually show your comparison between training and validation. There's nothing. There's even a bit more for the classical part, and the classical part trains much slower. And also the overall performance in terms of signal acceptance and background rejection is better for the autoencoder. And what we did is we did not limit the classical autoencoder to the size of the quantum autoencoder. We did a full hyperparameter scan. We made it wider, we made it deeper. We changed all kinds of hyperparameters essentially to make it more performant, and it didn't match the performance of the quantum autoencoder. There's something to be understood, obviously, but it's very interesting that this is possible. Actually, what you could also do is now look into the actual function that is mapped out by this quantum autoencoder and probably implement it classically to optimize your classical autoencoder. But it's definitely something that is worth understanding better. Okay, so this was quantum gate computing. Another quantum paradigm is actually the adiabatic quantum computing paradigm. I have like 10 minutes. Okay. So what does it mean? The adiabatic quantum computing paradigm is universal, as has been shown. And what you do is you encode your problem in such a form. You have a Hamiltonian, and you build on the quantum adiabatic theorem that if you have an initial Hamiltonian and you start when you set this to 0, so S of t is 0 in the beginning, and you start with your Hamiltonian HI here, for which you know the ground state. Then you initialize your state in the ground state, and then you adiabatically very slowly turn up S. So you go from the initial Hamiltonian to the problem Hamiltonian over a certain amount of time. And this is what you see here. So you slowly dial up your potential V here. You start in the ground state, and your wave function or your probability after measuring it stays in the ground state. So you can essentially, you're going to stay in the combined system of these two Hamiltonians all the time. And this solves a problem for you if this encodes a solution in the ground state of this Hamiltonian. So this is quite impressive, I think, to be used. The thing is, obviously, I mean, you do this, you need to have a long coherence time and these kind of things on a quantum gate computer. What you can use, however, is quantum annealing. So this one is not universal because it requires you to encode the entire thing as a Hamiltonian, as an Ising model. But on the other hand, it's accessible, right? You can use it on a D-Wave quantum machine. You get cloud access. If you sign up with them and your email address, you get about 1 minute to play with, which sounds little, but it's actually not so bad because your shots are microsecond times. So you have quite a few shots and test trials available. And what you do here is, as I said, you have to encode it essentially. This is your Ising model. It's a transverse Ising model where you can steer the humming and hopping across the Hilbert space by this delta t time-dependent parameter. And okay, so how would we now expect this to actually be beneficial for machine learning? Well, first of all, let's compare what does it different compared to a classical approach. Well, the thing is, there are metropolis algorithms, thermal annealing algorithms, for example, where you can also try to find a ground state of a complex landscape, energy landscape, for example. But if you do thermal annealing, you essentially have to go over the barrier and then down and hope that your state falls into the overall ground state of your landscape, of your energy landscape. Whereas if you do quantum tunneling, you can tunnel underneath the barrier. And you see here the scales differently with respect to the height and the width. So if you have a somewhat higher barrier, but a thinner barrier, then it might be under some circumstances beneficial to use quantum tunneling rather than thermal annealing, thermal going over the barrier essentially. So it really depends on the problem. And this is in general the issue, right? When we compare if you can actually hope for a quantum advantage in terms of in comparison to classical machine learning frameworks, there's not a very good theoretical underpinning of classical machine learning. So having a provable quantum advantage will not be possible because you already don't have a very good understanding of the theory of the classical algorithm itself. However, you can now heuristically look into different examples, and you can look into qualitative differences there, and then hope to extrapolate due to the qualitative differences that by scaling up the entire system, you will maintain these differences and hope for an advantage eventually. So how do you actually encode something in an Ising model? Let's start with the most simple example. The example is very difficult. It's an NP problem, but it's actually simple, easily implemented. So the task is we need to color in dots, either with white or with black. And the task is the dots that are connected with these edges, with these lines, they should not have the same color. So this will not be possible to solve this perfectly. The idea is then, okay, we pick some sigma IZ of your operator is -1, sigma IZ is +1 for colored ones. And so if I now forget about this term here in my Hamiltonian, what it wants is it wants to color in everything, right? It wants to have everything black because then I get a +1 here, and I reduce with every color dot that I have here the energy of my system further and further. Okay, this is not what we want. So what we want is we want to add a friction term here. So sigma I, sigma j, where I and j are linked via these lines, increases my energy if they are the same. So if I have -1 times -1, I get +1, increases my energy. If I have +1 times +1, I get +1, increases the energy again. So now I have again a potential landscape, and I want to find the ground state of this potential landscape in terms of my Ising model. Let's do something more complex, but closer to home. Okay, let's assume we have n² students that sit an exam in a squared room with n times n desks with a distance of 1.5 meters apart. Half of the students have a virus, the other half doesn't have a virus. How do we have to arrange them to minimize the number of infections due to 2 meters of social distancing? Of course, this is a problem we might have faced in the past. Let's see how we solve it here computationally. What you do again is you have this friction term here, and what you now want is you want to have, it's a minus here in front of this friction term. So you want to have the same people from the same cohort sitting next to each other, either both ill or both having the virus and both not having the virus. This would lower your energy of your system. And on the same, then you also have to put in boundary conditions because we don't allow for spontaneous healing or for self-infection. So put in these boundary conditions as well. Again, we have a potential landscape. And now we let it run, right? Now we let the computer calculate this, now using a classical metropolis algorithm. And for the computer, this is actually not easy because the computer has to sample from a 2 to the power 100 configuration space. So we probably can estimate what the best solution would be due to symmetry arguments and thinking about it. So the best solution would probably be one that minimizes the length of the edge, and a line is the shortest edge that you can have. There's a degenerate solution, a horizontal one, which you would find at 50% of the time. But for a computer, this is difficult, right? It's 2 to the power 100, more than you have nuclei in the universe and so on. Quantum annealing would do this very, very quickly, but this is, of course, a task that can be performed by a computer. So we have now seen how to implement a non-trivial problem in terms of an Ising model. Let's move on and do something that really interests us, namely implementing a field theory. So we want to do the same thing with an actual field theory. For that, we implement a potential. And we have this Purcell-Teller potential here, which has a time-dependent component. So you have this tangent square, which gives you your blue line here. And then you have your sec square, which gives you is time-dependent. And if you switch it on, then you have a deeper global minimum in your potential, which is displaced by V here, which is your, say, expectation value or so. So it's displaced here by the distance V. And what we want to do is now, we want to put this onto the quantum device, initialize classically, want to see if a wave function actually forms that corresponds to this potential. And if so, whether we can actually observe tunneling on such a device. But before that, we actually want to know what actually the calculation, the computational result should be. So you can calculate, of course, this whole thing using steepest gradient descent method for your action, and then you get a certain lifetime for your metastable state, which scales, the logarithm of gamma scales linearly with the displacement, V. But now let's make the experiment. Let's go to D-Wave, hijack their labs, and let's run something on their devices. Usually I would do this actually in real life, but my runtime is out. So I can only do it with screenshots, but it's very easy to do, right? They have an API, you just submit your problem, and it's written in Python and so on. So you would then initialize it, you would let it settle for 40 microseconds. And what you would observe is something like this, 2,500 shots or so. You initialize classically at this point. Then you do reverse annealing, you crank up the quantumness, and it actually forms the wave function that you would expect for the Purcell-Teller potential. And this is quite amazing, right? So this is the first step of showing you that there's quantum dynamics at hand. And then what you do in a second step is you let it first settle for 40 microseconds, and then you change your potential. You can do this during runtime. This is the nice thing. This kappa k of t is a time-dependent variable that you can switch on while it's running. And then you make a deeper minimum, and what you see is then a tunneling actually occurs. So you see it finds the deeper ground state, and after a certain amount of time, here 100 microseconds for a fairly displaced thing, it finds this tunneling solution. Now you can compare whether this actually agrees with what you calculated, whether your metastable state in your theory has the same lifetime that you can observe here on this quantum device, and it follows nicely this shape. So this is the calculated solution, the fitted curve. And you can then compare essentially the original data, and you find a reasonable good agreement. It's not perfect, it's not next to leading order calculation, but it's a reasonable agreement with which you see here on these devices. So this also helps to believe that there's genuine quantum dynamics at work. Of course, you look here into tunneling, which actually doesn't rely too much on a coherence effect of your quantum system. But the next thing is you could, for example, also imagine to actually solve this, because this model that I've just shown with the Ising model is actually continuous time quantum annealing. So you can do time slices as well. And one thing would be you can, of course, calculate the time-dependent Schrödinger equation. You put this potential again you calculate it for your potential, and you initialize with the Gaussian. So what does not happen is that the Gaussian moves just to the center and stays there, right? This is not how quantum mechanics works. It actually slouches over. So this is the solution, the time-dependent solution at T23, T38, and whatever. So it slouches over, it comes back and forth, it kind of interferes and so on, and then after a certain amount of time, at some point, it will settle into the global minimum here. And interestingly, if you do this on a two-dimensional example here for D-Wave, we look into this potential here. The global minimum is at, I think, 0, 4 or something like that. And we initialize at 0, 0. There's no boundary now, so it's not a tunneling process, but this more corresponds to a second order phase transition, if you like. So what you see is this: you do time slices, you record the hits that you observe, and it starts at 0, 0, and then it slouches over, like we discussed before, like it should do when it solves the time-dependent Schrödinger equation, and it goes into the global minimum at 4, 0. So also interesting. Okay, So still not there, right, for machine learning. We wanted to discuss why we actually want to do this for the improvement of machine learning. And so the next step is now to look into and compare actually classical optimization tasks with quantum optimization tasks. So common classical optimization tasks, ground state finding is gradient descent, Nelder-Mead, and thermal annealing. And we want to compare it with quantum annealing. So what we put onto the device is essentially a two-dimensional multi-well potential. The global minimum is at 0, 0, and then you have plenty of local minima. And now you compare these 4 different techniques, and you see here the distribution. This is a probability distribution of what you measure. So you see that Nelder-Mead, gradient descent, and thermal annealing, they get stuck in local minima. They end up there, they go and find their way out. They say they finished training essentially, and then they stop there. This graph here shows you how close you made it to the global minimum depending on where you started. So the dark blue one is 0, 0. This means from here, everywhere they made it into the global minimum. But starting from up here, you have a light green or something. So the distance is 2.5. So it probably got stuck here or here in one of these local minima. So it didn't make it into the global minimum. This is what these colors indicate. And now for the quantum part, you reliably and very quickly, as you see here as well, and the time that you are running in microseconds, very reliably find the global minimum of your system. And this is, of course, interesting. This shows a qualitative difference because quantum tunneling allows you to go there without very fast and reliably. And the question would now be, can we actually use exactly this feature for machine learning? So as we said, machine learning had 3 different parts. It's a complex self-adaptive system. It has a loss function. And it has an optimization part, essentially, which finds the ground state of your loss function. So we also said that the loss function itself that you actually need to use to train the neural network is nothing but a function of functions, right? That's all. It's a function of functions that depends on trainable parameters. So why don't we put this function of functions onto a quantum annealer and then use these dynamics, these quantum dynamics, to actually train the neural network? The advantage is you can use the same trainable parameters. You can potentially even use, so I'll talk about the activation function in a second, but the point is what you want to extract is actually the position of your global minimum. You don't want to know the height of your global minimum of your loss function. All you want to know is the position of the global minimum of your loss function, because those are the trainable parameters. You can read out. And then for deployment, you don't want to use in your phones a quantum computer, obviously, right? But you want to use a classical machine learning framework. So after you extracted the trainable parameters, quantum mechanically, reliably, quickly trained, optimally trained, you want to put it onto a classical device and use it there. And this is what you can do. For deployment, you want to run a classical machine learning framework. And so you do this and you put in standard, benchmark data, essentially, you find everywhere, and you can do this for a ring. This is the decision boundary that you get after training on a D-Wave machine. A background signal, it's nicely separated. Of course, they are fully separable here. This is fully separable. And this here is not fully separable, but it still finds a decision boundary that looks good. And also this in TT bar example, for example, it also is not fully separable, and it gives you some decision boundary here. Now, if you compare, so to be fair, this is a constrained classical neural network. So it's not a full neural network, but this constrained classical neural network to the size of the quantum network, to the size of the network that was trained on a quantum device, you get very often stuck in a local minimum. This is why you see here these uncertainty bands, because not very often you get a perfect training. Perfect training would probably be up here. So again, the quantum network trains very reliably, perfectly, whereas the classical one that is constrained does not, and has a large variance, because depending on where you initialize it, it gets stuck somewhere in a local minima. So the thing is, if you have a non-convex problem, then those are, of course, critical issues, right? That you never know if you have trained your network optimally, if you are stuck in a local minimum, or if you actually made it into the global minimum of your loss function. For convex problems, this is it's not a big deal, obviously. I mean, there you know that if you have an extremum, it's the global minimum of your problem. Okay, so knowing this, okay, so we know we can actually train neural networks. What I said in the beginning is also, well, it's an optimization task. And the thing is, you can actually phrase every problem that you want to calculate as an optimization problem. So here, for example, this is a function. This is a functional that depends on some function phi with some derivatives and so on and so on. If I have some equation that's x squared plus x equals 3, I put the 3 on the other side. I say x squared plus x minus 3 equals 0. We already have an optimization problem. Namely, I want to find x so that the left side is minimized to 0. And you can put this as a loss function on your neural network. It's you have here a differential equation, if you like, partial, coupled, whatever differential equation. You put this onto your neural network as your loss function. You put this down with boundary conditions. And then again, the goal is to minimize, to find the solution, your neural network output in such a way that the neural network output minimizes the entire loss function. And then the neural network output provides you with your solution to your problem. This is exactly as we said before. We want to encode the problem or the solution of a mathematical problem into the ground state of a very complex and self-adaptable system. Not into a protein, but here into a classical setup for a neural network. Okay, and now, because we can train it also on a quantum device, and we can train it classically, if you like, you can have a look. Our code is called LVET, classically, and QUADE, quantum mechanically. You can, of course, now have a look, and these codes would, in case you had access to a D-Wave machine, you could run it there. They solve differential equations. Of course, the classical part can do much more or more complex classical differential equations. So this is what you see. So both of them, however, do reasonably well. And you do this for fitting. If you're into fitting, you can also, if you have a non-convex function for your fitting framework and EFT and so on, quantum annealing is fast, minuet slow, and the chi-square value, in case it's not a convex problem, is large, so it gets stuck frequently somewhere else. This is also again here an example where you see the benefit of quantum tunneling over gradient descent or some other classical optimization tasks. And lastly, I just want to slightly overrun, but lastly, I want to point out that you can do this on an Ising model. But as we discussed, you can also do this with adiabatic quantum computing, which is universal. And this actually allows you to encode the entire problem with much less qubits. The problem is currently you can't really run this because you need a process that is in coherence. And here you actually need coherence because this is not a tunneling process. It's actually a process where you start in the ground state of one Hamiltonian for which you know the ground state, and then you dial up the Hamiltonian into 2 Hamiltonians until you reach the ground state in the problem Hamiltonian. And so you encode, again, this is a potential function. You put your loss function into V, and then the neural network output that goes into your loss function is just the entire function that defines your neural network. And then this is the combined Hamiltonian that for which you need to find the ground state. And then after doing this, you can read out the axes and use them in a classical neural network that is optimally trained. All right, so that's it. So it is a bit of a potpourri of stuff I discussed, but I hope that these 3 categorizations where quantum computing could potentially contribute beneficially to particle physics has covered a little bit of ground. So on the one hand, the simulation of field theories, then the simulation and improved simulation of actual collision events, and third of data analysis techniques in terms of machine learning frameworks. In my opinion, at least, quantum computing is an exciting research area. And I think what I was hoping to show today is that already now you can actually do quite a few interesting things on actual devices, but also on simulators. And people will, of course, continue thinking about new frameworks and new computational techniques that can then be used on near-term noisy quantum devices. The thing is, of course, however, if you want to actually apply all of these kind of things to actual real-world problems these days, then the quantum devices are still not mature enough to actually solve actual real-world application, or to provide actual real-world applications to problems that we are interested in. So they need to grow in terms of size. The quantum volume needs to grow, needs to be more fault tolerant, and all the operations that you actually need for potentially universal quantum computing and so on also need to be available on these devices. Good. Yeah. So, I mean, the thing is, I also recognize that I'm the only and last person to stand between you and your Florentina steak. So, of course, I'm going to be around, and we can, of course, discuss this also any day of the week. So,
I have a very small question. In the first part, in the one that you are doing universal computation, not in the annealing, when you go to the real computers, have you applied any technique of error mitigation?
No, so for all of these applications, we have not applied any error mitigation so far. And for the machine learning part, where we had a very shallow circuit, you have seen that this didn't matter. So the accuracy essentially remained the same. But of course, this would have helped for the particle shower simulation and so on.
In my experience, it's amazing how much you can recover.
Oh, really? Okay.
So all these applications don't use any even simulated quantum memory. I mean, there is no such a thing as like storing all the data in a quantum memory thing. So all your data are classical, and they're going through your.
Well, okay, so this requires probably a lengthy answer. So the thing is, it's true for the machine learning framework, the quantum variational classifier I just showed. You have classical data, you read it in, you put it onto, if you like, a quantum device or a simulator, essentially, and then you evaluate your variational quantum circuit. And then you update it in a hybrid form, essentially, and you train this entire thing. And obviously, this is very inefficient, right? You would like to have this on a quantum device. It has been shown that a quantum algorithm, a quantum machine learning algorithm acting on quantum data provides an exponential, or can provide an exponential speed up over classical approaches. So this is really when you are essentially sure that you will do better using a quantum scenario than a classical scenario. Now, here, however, speed is not necessarily the only metric for machine learning to actually improve on classical approaches. As we have seen, for example, the quantum autoencoder, it's also classical data, right? You are not necessarily, when you train something, this sits somewhere. Some data scientist will sit there maybe for a year, train their network and so on. So time and operations is not necessarily here the crucial factor, but maybe to get the decision boundary right for your signal and background sample is more important to have an actual accuracy of your algorithm, to have a better ROC curve and a better performance in this way. So it's not only the question about speed is important if you have if you want to actually argue about actual performance in terms of calculations, but for how reliable I find the ground state can be more important than the actual time it takes to run on the device itself. Yeah, just shoot.
So there's superconducting, trapped ion.
Yeah, okay. Yeah.
Quantum machine learning.
Exactly, that's right.
Machine.
Well, I mean, I have only, so if I should speak from experience, I can't really, because I only had access to the D-Wave machine, which is just a quantum annealer, and then IBM machine. So ion traps are much longer in coherence. but the problem is they have much fewer qubits and so on. They have their own problems. If you steer them with lasers and so on, there's interference effects and these kind of things. So, and then on the other hand, superconducting qubits, coherence time is much shorter, but by now you have quite a few of those in these devices. But you are right, I think for the machine learning tasks, the problem is not so much the noise, because you optimize anyway in some way, right? You try to find the minimum of your loss function, and it's not the biggest problem there. Yeah.
Thanks. I maybe had another question, if that's okay. So you also mentioned you can do optimization with quantum annealing, and then you also have this approximation, the QAOA algorithm on gate base.
Yeah.
In your experience, if I'm trying to solve like an icing optimization problem, would it be better suited? D-wave annealer, quantum annealer, or are there instances where Q is better? I just thoughts on, is this known, or should you just try both?
I think this is heuristic, just like everything there. Yeah. I think it's not a theorem or anything like that.
Yeah. Okay, thanks.
Okay, thanks everybody. Thanks to Michael again.